So, in the last lecture we discussed about the concept of single degree of freedom system model. We have also discussed about the essential characteristics or essential features of a single degree freedom system model, and we said this model is an idealized model because we are allowing the mass to move only in one specific or desired direction of displacement. Single degree is not called a single degree of freedom system because the mass is lumped only at one point. It is not because of this factor, it is because of this factor that the mass is allowed to move only in one specific direction, remaining all directions are restrained. We impose an artificial restraint in all other direction, and then when we have a model like this, we say the model essentially will have the elastic restoring force. It may be a matrix, it may be a single value, it will have a mass component which will represent the inertia force in a given system. It will also represent some frictional components and material loss which will have been identified by damping, and of course you will have the external force which is a function of time, which is essential characteristic of dynamic loading otherwise in the analysis. We also said in the last lecture that in a given analysis format in dynamics you can also eliminate C, eliminate f of t, but k and m should be always present. You can subdivide them into 4 categories and saying that free vibration analysis undamped, forced vibration analysis undamped, then damped free vibration and damped forced vibration. Depending upon why we cannot eliminate k and eliminate m in our whole analysis, we discussed this. Then we had a question that in how many formats we can actually have an idealized single degree of freedom system model. So, essentially the first model was, as we discussed yesterday, is a spring mass system. I can have a damper here, may not have a damper here, I can apply f of t, may not apply f of t. This is what I call as spring mass system. So, the system now will have only one direction of displacement which is x of t. So, it is obviously a single degree of freedom system, not because there is only one mass point, but there is only one direction of freedom or the degree of freedom where we are allowing the displacement for the mass. The second could be a torsional pendulum. Let us say pendulum have some thickness, and let us say the diameter of the pendulum is a, this is theta which will vibrate, therefore theta is going to be the degree of freedom. In this case, this is what we call as a torsional pendulum. So, what does it mean by this example is that the displacement may be translational, may be rotational also. The third idealized model could be a spring mass pulley system as you have here. I hinge the pulley here at this point and allow the rope to fall through this and have a mass suspended here. If I say the radius of the pulley is a and the angle of rotation is theta, then the mass will also move as, let us say for example y of t. Then from this problem we may wonder there are two mass points concentrated. First is the mass of the pulley itself, the second is the suspended mass m. So, I can call this as capital M for our understanding. Does not mean that capital M denotes a matrix and small m denotes a element of a matrix. Capital M denotes mass of the pulley and small m denotes the mass of the object which is suspended from the pulley by a string or a rope. K of course denotes the elastic spring force what we are having here, and there are two mass there are 2 degrees of freedom like theta and y. Why do we call this as a single degree idealized model? Now there is a combination between this y and theta. I can simply say y can be expressed as a sin theta. So if you look back the definition classically for degrees of freedom, we already said it should be number of independent displacement coordinates. I must not be able to explain the connectivity between the 2 degrees. As long as the connectivity exists, either I call y as my degree of displacement or freedom or theta as degree of freedom. So either one of them, because unfortunately if you know one, you can get the other automatically. So they are not independent to each other. So therefore even though this has 2 mass components, it appears there are 2 degrees of freedom as rotational translational, but this is an idealized model of a single degree because they are not independent. They can be expressed when one is known. Okay. The fourth model is a vibration isolator. I have a mass, let us say m1, series of springs. I am just showing an example of a spring and I am showing a dashpot also here, and I have another mass which is fixed to the base here. So there is a mass component here, I can call this as let us say m2, there is a mass component here. Of course there are stiffness components and there is a damping component here, and there is a possibility that this mass can also vibrate and this mass as well as can also vibrate independently. Why? Because these motions cannot be exactly same because they are connected on resting on a spring which is restoring the action on mass m1 with respect to m2 or m2 with respect to m1. On the other hand, it is very simple for you to realize if m1 and m2 rest each one of them solidly like this, then if you mark this as x1 and this as x2, then you will not agree because m1 and m2 will have a rigid body movement. But I am separating m1 and m2 and putting a spring in between which is having an action of restoring. Therefore the relative displacement, the displacement of mass m1 can be different from that of mass m2. Okay, but still why we call this as single degree of freedom? Because I am interested in expressing the relative displacement. Now the question comes, relative displacement of what with respect to what? Displacement of mass m1 with respect to m2. So I have only one degree of freedom here. Okay. So these examples are standard idealized models of single degree of freedom system, mathematical models which clearly tells me that each one of them have independent degrees of freedom or displacement coordinates which will help us to significantly identify the inertia contribution on these models. Okay, here as well as here, and this gives me another crude understanding as for a single degree of freedom system. Generally you should mark the coordinates of displacement like here, like here, like here, like here at the points where mass is concentrated. On the other hand, I would not like to measure the displacement with respect to any value from here. It means coordinates are generally grouped or lumped at the points where mass is concentrated. So obviously if you have a system where there are 2 mass points, there will be 2 coordinates. So this is a correlation between where do you want to measure and how do you want to measure. How do you want to measure is an idealized constraint imposed by the model, it is a single degree. Where do you want to measure is an understanding to make the problem easy. Now you may ask me, if you do not mark the coordinates of displacement at the mass points, what would be the difficulty? We will answer this slightly later, which will have a coupling effect on the mass matrix itself. When you talk about 2 degrees of freedom, we will talk about this. If you do not measure the coordinates of displacement at the points of mass lumping, then the mass matrix will have a different indication in your analysis. In general, by and large, it has got great advantage of marking the displacement coordinates at the point where the mass are lumped. That is what we understand from this discussion now. Okay. So, all these 4 are standard idealized mathematical models of single degree of freedom system. It qualifies to the force is a function of time in all the cases and the body do vibrate in all the cases. When the body vibrates, the body has a specific frequency. We would like to estimate that frequency as one of the essential outcome of this vibration of the body, and of course mass has to be present, otherwise I need not have to do a dynamic analysis at all. And we all agree that this displacement component function of time in all the cases is significant, otherwise we could even do a compensatory static analysis for this. Okay, that is what we have understood. Is this clear? Now the fundamental question comes is, after I idealize a mathematical model in the format of 1, 2, 3 and 4, what I am looking from this model, what would be the first output from this model? The first output what I do is, I must write equation of motion for this model. You may wonder why I should write an equation of motion, because I am interested in displacement of this model at any given point of time. So in this equation of motion, the variable will be obviously with respect to time, it is a time variant value what we will write. So let us try to write down the equations of motion. There are many methods by which you can write the equation of motion for a single degree and multi degree as well. We will start with, we will explain all the methods quickly, then we will select few methods amongst this and keep on applying them in the problems and try to write the equation of motion. So the first step in solving a dynamic analysis problem is that you must idealize or pick up or choose a specific idealized model, maybe single degree, maybe multi degree, pick up the model, then for that model write down the equation of motion, then solve the equation of motion. That is the first outcome what I will get from this analysis. So there are many methods by which you can write equation of motion. You can use simple harmonic motion method, what we call SHM method, to write the equation of motion. You can use Newton's law of motion, you can use energy principle, or I will put this energy method, you can use Rayleigh's method, you can use what we call D'Alembert's principle. There are 5 methods to write down equation of motion for any mathematical model. I am going to apply this for a single degree of freedom system model to start with. In all these models, as you just now saw, these are all discrete mass points, okay? They are not continuous. So what does it mean is, my variable will be only with respect to time, not with respect to span, because the mass is not distributed uniformly along its span, along its length, etc. We are lumping the mass at any specific desired point of our interest. Obviously, which will be the so called point of interest in this given mass? It will be that point which will be the center of gravity at the mass center of this body. Okay, it is as simple as that. So if you look at the simple harmonic motion has got 2 rules which we all studied earlier in physics. The simple harmonic motion has a basic characteristic, the acceleration will be always proportional to the distance or the displacement of the particle, to the distance or displacement of the particle, I put as body, measured along its path of motion, okay, along the path of motion. That is the first characteristic of SHM itself. The second characteristic is the body will be always directed towards the equilibrium position or towards a fixed point, and hence this direction generally will be opposite to its motion. I use this characteristic and write down the equation. So, we already said acceleration is proportional. So, x double dot is proportional to minus of x. There are two reasons why I am putting this equation. X double dot is proportional to x, that is what one of the important characteristic of simple harmonic motion. I put negative sign because it is always directed to the force opposite to its motion. So, I should say this is equal to rho, some constant of x. So, I can say x double dot plus rho x is 0, and people can advise this constant to be omega also. We are not worried about that, it is a simple proportionality constant. So, what we infer from these equations are the following: it is a second order ordinary differential equation in a time domain, okay. Because as we understand, if x is the displacement, then dx by dt, which I call as x dot, is the velocity, and d square x by dt square is again dx dot by dt, which I call as x double dot, is the acceleration. So, these are all differential equations in time domain. So, I can simply write equation of motion using a simple harmonic principle using these two characteristics of the motion otherwise defined also, okay. Let us look at the Newton's law of motion. Any question here? Which method we will apply we will see, but we will like to see all the problems in a simple manner first, then we pick up varieties of problems and try to apply any one of these methods and see can I write the equation of motion using this method. I will pick up this now. Let us do for the second method using Newton's law. We will demonstrate this method using a very simple example. Let us say I have a spring, no weight is attached to the spring, okay. The moment I attach a weight to the spring, the spring will elongate. I am attaching some weight. I call this initial elongation of the spring, let us say as x naught. And what will be the resisting force in this case? The resisting force in this case will be the elastic restoring force offered by the spring, okay. If I then apply a force here, pull the string and leave it, at any instant of time this will be my displaced position of the mass, which is again W. So, I want to now draw a free body diagram of this at this instant and then apply Newton's law of motion to this. Can you try to do this? Draw a free body diagram of this, write down all the forces of this, because this is acting down, and the restoring component is basically k of x0 plus x in this case. So, if I apply taking this as my positive sign, this as my positive direction, I can say plus W minus of k of x naught plus x is the net force. As per the Newton's law of motion, this should be equal to mass into acceleration. Okay. Now, we already know from the first case that the extension caused by the load on the spring, which is x naught, should be compensated by the stiffness of the spring multiplied by x naught itself. It means as W will be equal to k x naught from the initial case, I will get this equation as minus k x plus is equal to mx double dot. So, mx double dot plus k x is 0 is my equation of motion. So, we infer an important information from this. If you want to write equation of motion using Newton's law, what you should do is ideally represent all forces the vector quantity, right. You have to mark the directions also, not only the magnitude but the direction also, all forces, then sum them up in vertical, horizontal, any desired direction and write equation of motion. Okay. So, when you are trying to represent all the forces vectorially, this is what we call as free body diagram. Okay. Draw a free body diagram, represent all the forces internally as well as externally acting on the body, then sum them up vectorially, maybe vertically, horizontally, etc. Use a specific sign and symbol, add them up, and then you will get what we call equation of motion. Again you will see there is a comparison between this equation of motion and what we got in the previous example. This is also a second order ordinary differential equation in time domain. Okay. Let us look at the third case where we will write equation of motion using energy principle. The energy method can be applied only to a conservative system. It can be applied only to a conservative system. What do we understand by a conservative system? Energy can neither leave nor enter the system when the system is under operation. Okay. So, we will not consider any loss in the system. So, let us look into only two components. One is the kinetic energy component, which is of course a function of velocity. Other is the potential energy component, which is of course a function of displacement. So, I can write kinetic energy expression as half m v square or half m x dot square. I can write the expression of potential energy as half k x square. Why we are using, by the way, half here? Average, because you know wherever kinetic energy is maximum, potential energy is minimum or 0. On the other hand, vice versa, I am looking for an average value. Is that clear? That is right. It varies from 0 to maximum, looking for the average value. So, half mv square or mx square and half kx square. Now, the total energy, since I do not have any other contribution and it cannot allow me to enter and exit because it is a conservative system, the total energy I have is a sum of kinetic energy plus potential energy since the total energy cannot vary, I can say the first derivative of this with respect to time can be set to 0, is it not? To have it maximum, then the second derivative should be negative, or to have it minimum, second derivative should be positive. That is the second issue, but the first derivative should be set to 0. Okay? Let us do that here. I will differentiate this too with respect to time again and see what happens. So, d by dt of half m x dot square plus half k x square should be set to 0. So, which will give me half m 2x dot x double dot plus half k 2x x dot set to 0, half goes away, x dot is common. So, x dot of mx double dot plus kx is 0, x dot cannot be 0 because a displacement is happening, so velocity will exist. So, mx double dot plus kx is 0 is my equation of motion from the energy principle. So, what we learned from this case is this can be applied only to conservative systems. It works on totally on energy principle. So, you should be in a position to compute different components of energy in a given system. In my case, I have taken example of only kinetic and potential. There can be dissipation energy also, which is a function of damping and velocity, which we will add later. Okay. So, I keep on adding them, I apply the same concept, can write equation of motion. What I have got to do is find these components, add them, take a first derivative with respect to time, sum them up, you will get the equation of motion. So, this is an easy principle. So, this is a very common principle applied for systems in advanced dynamic analysis and applied mechanics schemes, okay, where we focus on energy methods. There are many, let us say, counter arguments of using energy methods for dynamic analysis. If you are looking forward for any response control of motion based on dynamic characteristics of a structure, you must do the dynamic analysis on energy principles. For example, I am looking for a damper design in a given building. I have a building subjected to earthquake forces or any lateral force, maybe even wind. I want to control the response characteristic of the structure in time domain. When I am looking for any kind of control of energy, I must use my dynamic analysis in energy method. If I am looking for identifying the response, not the control, I must use force method, which is Newton's law. Okay. So, people divide themselves in two different groups and start writing equations of motion in their own manner, can always cross them and verify, because they have been getting equations of the same order whatever method you apply, but it depends upon preferentially which method you want to employ for a specific type of a problem. Okay. That is why you will see generally, if you look at research papers which talk about response control of structures, talk about emphasis on relative motion of the body based on viscous dampers, etc., you will find the equation of motion generally written using energy principles. There is a software which helps you to write equation of motion and solve the equation of motion for a multi degree, which is a freeware available developed by University of California at Berkeley. I will link that software as we proceed further. It is a freeware available, you can also download the software easily, and you can also easily find out the frequency of vibration of a multi degree freedom system model up to 3 instantaneously. You can also see the animation of the model, that is a very interesting part. I will run that software here for you, you can also download, I will give you the link, you can download the software. It is actually a patented software developed by University of California Berkeley Civil Engineering Department on earthquake forces. So, we will use that. So, it will have both the methods, you can develop the equation of motion and solve it using Newton's method as well as using energy methods. Then you will see the difference where in which case you will use what kind of method. Okay. The question is, we are talking about not the solution of it, we are talking about how to write the equation, but I am giving one step ahead and saying if a solution is interesting based on some response control, you must write the equation of motion using energy methods. There is no set and hard and fast rule, you have to follow a specific method for a specific application. It will be comfortable for you to do the problem or analyze the system if you follow the following techniques, that is what we are trying to say. Any questions here? As we are not considering the loss of energy in a given system. Dissipation is basically loss, okay, it is a loss of material, loss of energy, right.
That is not the grounded value.
Yeah, I mean in this particular example, in fact in all the 3 examples I have not taken the frictional component at all. C component I am not modeling at all, I am taking only M and K, basic model. We will also do problems where C is present, as I showed you, C is present, we can write the equation of motion, we will do that, but to start with let us first understand the basic model. We all agree that K and M has got to be essentially present, otherwise singular freedom cannot be modeled. So, we are using that first to understand, then we will include the dissipation energy also and we will try to model it, no problem, we can do that. In this example I have ignored it, okay. So, we will pick up now the Rayleigh method. Rayleigh method is an extension of energy principle. We all know that whenever or wherever in a given system kinetic energy is maximum, potential energy is minimum or 0. On the contrary, wherever potential energy is maximum, kinetic energy is either minimum or 0 in a given system. So, the Rayleigh method simply says maximum potential energy should be equal to maximum kinetic energy in a given system. Use this algorithm and try to write equation of motion. Potential energy maximum equate to the kinetic energy maximum in a given system, which will be of course equal to the total energy of the system. Using this principle you can write equation of motion. I will demonstrate a problem later subsequently using energy method, at that time I will extend the study using Rayleigh's method also for given examples, okay. So, nothing special about this method except that it is following the same algorithm as that of an energy method. The only clue here is do not look at the average there, look at the maximum value here, that is all. Let us look at D'Alembert's principle. It is a very interesting example or a method defined by scientist D'Alembert. See, people felt that the dynamic analysis is getting complicated because of time variance in nature of the response and because of complications introduced at different levels or different kinds of writing equations of motion. What D'Alembert thought is, can I convert the dynamic problem can I convert the dynamic problem into an equivalent static problem? So, D'Alembert actually did it. He converted the dynamic problem into an equivalent static problem. Therefore, this is imaginary. Cannot be applied to real systems. It is a concept. Let us see what is this concept quickly. This will also give you equation of motion, but let us see how this concept can be understood. Let us say I have a spring mass system like this. Which is having, let us say, x of t, I take this as positive. So, initially I will remove this, the spring is, or the spring mass system is at rest. Initially the spring mass system is at rest, it is at rest. Apply a force, maybe f of t, and the mass is getting displaced by, let us say, a value x naught. So, apply f of t, the mass or the spring mass system gets displaced by x 0 as shown in the figure. Then these are all spring stiffness k, and mass m. I release this force and the mass will vibrate. Mass vibrates at any instant of time, let that be x. Let us quickly draw the static condition of this system at any instant of time. I have a mass which is represented as m, when I try to apply the mass or pull the mass and release it, the only force which is counteracting or helping me to restore the mass movement is k of x. In the whole system I have nothing except the stiffness attached here, the spring attached here. If I try to pull the mass and release the mass by an external force f of t for instantaneous time, the only remedy or rescue force what I have to bring the mass, to attempt to bring the mass to the back to normal position, is the restoring component coming from the spring. So, I am marking it in the opposite direction to that of motion of the mass. So, you have seen in this example that initially I moved it and I got a displacement x naught, I release the force, at any instant of time t it is not coming back to 0, it is displaced by a value of x. Now, imaginatively if you want to bring this back to 0, I must apply an additional force in the same direction as that of the elastic restoring force to bring it back. That force will be mass proportional acceleration of this. So, I must say apply an imaginative force which will be mass proportional acceleration of this, because that is what Newton law says, that is a force. Apply it in the same direction as that of the restoring force, or apply in the direction opposite to the motion of the body to bring the body to the normal condition. Now I write equation of motion for this applying a static condition, because it is now static, at any time instant I have this value. Is it clear? So I simply say minus kx minus mx double dot is 0. Why 0? Because the body has been brought to rest. So on the other hand, mx double dot plus kx is 0. So I get equation of motion from D'Alembert's principle, which is a concept and cannot be applied to reality, because at any instant of time mx double dot will be keep on varying. If you really want to bring this mass to rest, you must have a program controller which will be keep on measuring the displacement any instant of time and provide a force opposite to the motion of the body, which is proportional to the acceleration of the mass at that time, and this will be keep on varying, is it not? So you can use this technique for devising or designing control algorithms, what we call as intelligent structures. You can design actuators which will apply force which is mass proportional to acceleration of the body at that instant of time, develop a time history and keep on trying to bring the mass to the normal position. So what do you understand by bringing the mass to normal position? It means the mass is brought to rest. The moment the mass is brought to rest, dynamics does not apply. So D'Alembert converted the dynamic problem into an equivalent static problem using this technique. It is very easy to apply this concept for a single degree of freedom system model. It is very difficult to apply the concept for multi degree, because you do not know which mass you want to tune. If there are more than one mass points, if there are more than one coordinates of individual displacement, you cannot tune which mass and which coordinate you want to. So this concept cannot be blindly applied more than a single degree freedom system model. So in that way one can say this method is not popular. There is nothing drawback in this method, it is not popular because of this constraint in applying this method for higher order problems. Okay. Any questions on any one of these methods? So now I am capable of writing equation of motion at least for a single degree freedom system models of any example given to me by applying any one of these methods and try to write down the equation of motion. Okay, 5 methods. So choice is yours, you can do. I will give a tutorial, I will print the tutorial in the next class, circulate it to all of you. I will give about 40 problems on single degree freedom systems, different models. You have got to solve them, you have got to write the equation of motion, and what I mean by solving it is what I am going to discuss now. Okay. You have got to solve them and show me. Need not submit, but you have difficulty, we will solve the problem here. If you do not have difficulty, we will just go ahead with higher complication systems. Okay. All these problems will be single degree. Remember that I have idealized them in my own method based on the 4 mathematical idealized models which I showed you in the beginning of the lecture. So it will be one amongst these models. Identify the model, pick up any specific method of writing equation of motion, write the equation of motion and solve it. So what do you understand by solving this? Any questions here? So let us pick up a general equation of motion for a single degree which is written like this. For an undamped free vibration. Why free? Because f of t is 0. Why undamped? Because c is 0 here. The damping content is not present in the equation of motion. I can rewrite this equation by dividing by mass the whole equation, x double dot plus k by m of x as 0 omega square is k by m, where omega is called the frequency of vibration of the system. Since it is free vibration, people call this as natural frequency, and people put a suffix omega n. Okay. So, the units for omega n is radians per second, which we call as circular frequency or angular velocity. Angular velocity in radians per second. Can also have f as cyclic frequency, where the relationship is omega is given as 2 pi f and f is 1 over t. So, the solution, what I mean by single degree of freedom system is, I am interested to know my frequency of vibration or period of vibration. So, the problem is you must draw the given idealized freedom single degree of freedom system model, write down the equation of motion, identify the coefficients of x and x double dot in the given equation, bring it to this normalized form and get this value, and that will be equal to your omega n. That is what we will be solving this. Okay. So, for omega n to be obtained for a single degree, it is as simple as that. I must try to get the coefficient of this particular value of the displacement, whereas this is going to be unity, that will give me omega n directly. And as we all understand, why we are bothered about omega n, because I am interested to know whether this omega n by any chance will get tuned with the forcing function on the right hand side, which will act on the system. This forcing function, which is a function of time or frequency, can be a wind load, can be a wave load, can be a current load, can be a load additional due to marine growth, can be an earthquake load, etc., which we already seen in the last lectures. So, my principal objective is whether this omega n will match in the bandwidth of omega of my excited force. Suppose if we know that, what will be the great thing which I will get an advantage of this? The greatest advantage we will get is, first I will know whether my body will resonate or not, because when these two frequencies get tuned, there is a possibility of getting resonated. The response can shoot up to infinity, okay, can shoot up. How do I control? There are two methods of controlling it. One, push omega beyond omega n, or push omega n beyond omega. Which control can you do? Omega is a natural phenomena which is coming from the wind, wave, etc. Therefore, we have no control. We cannot put a ban on a structure saying the structure should not be excited by omegas of the following bandwidths. So, God please note, that is not possible. So, we can control omega n. Controlling omega n means I have a full liberty to design a structure whose mass and system stiffness can be tuned, and mass comes from the geometry and stiffness comes from the arrangement of members, which is actually the design. That is why we said offshore structures are form emerged design, not function. Form means cross sectional dimension and material which is giving me mass, also arrangement of the members may be 3 legged, 4 legged, 8 legged, etc., which gives me the stiffness. So, if I know my omega bands which is exciting my structure, if I know my omega n, being a single degree freedom system, can easily push these two bands apart so that my structure will not get resonated. Now, the question comes very interestingly, you may ask, sir, omega is not under control. There is a possibility omega with all these so called intelligent exercises may still land up in matching omega n. Then what will happen? We will answer this further later.